We're going to continue talking about Mars and asteroids. We might get to Jupiter. We'll see. So, getting started. The moons of Mars. Fear and terror. They're supposed to be twins according to mythology, but Phobos, fear, is 7 times bigger than Deimos. So they're not really what we call identical twins at the very least. These are the 2 moons of Mars, which of course you saw in your activity last night in lab. And of these moons, neither one looks anything like our moon. Their sizes are small. Both are less than 20 kilometers across. So basically, just a little bit bigger than the city of Lincoln, right? Now, if one of these were to hit Lincoln, it would cause a lot of damage because, of course, the air energy would be very large. But they're, excuse me. It would cause extensive damage because you'd throw up enormous amounts of material into the atmosphere. And so it'd be very damaging. But these don't look like our moon. How do we believe something like this would become a moon? Now, what's the theory on how our moon became our moon? Something hit us. We look at these and we don't get the idea that these are something hit Mars and stuff flew off. And so that's one that people just pretty much throw out. That's not what it would look like. I probably have stuff in my teeth. I'm sorry, I just finished eating, as Max can attest to. I can feel the corn that I ate. That's what I'm saying. So that's unlikely. Another option is formed together with Mars. But it just doesn't look like anything that would have formed together with Mars. So the third conclusion is the one that we tend to believe, that these were asteroids, which is the topic coming up right after this. These were asteroids that were collected by Mars. So basically they came flying by a little too close, and Mars's gravity pulled them in and held on to them and didn't let them leave. So that's the prevailing theory about how Mars got its 2 moons. Now, when we go out to Jupiter, we'll see that Jupiter has the 4 what we call Galilean moons, big moons. Saturn has only one that I remember, big moon, but they have just a huge number of smaller moons that are like these, that are once again believed to be objects that came flying by and got too close, and the very strong gravity of these massive planets held on to them and brought them into orbit. So let's talk about the asteroid belt. So for starters, the first asteroid was discovered in 1801 by Giuseppe Piazza. I think that was Piazza, right? Yeah, Piazzi. I was close. And how Giuseppe found them, and I hope I'm pronouncing that name right, is kind of interesting. There is a law called Bode's law. Here I have it written as Bode's rule. Sometimes I think it's Titus Bode law. And what it says is that the planets have a nice, orderly distance from the sun. And that orderly distance to the sun comes out to be 4 plus 3 times 2 to the n divided by, that's not a 10, 10, that's still not a 10, in units of astronomical units. That's where the A kept coming up that I was writing. Where n is equal to minus infinity, comma 0, comma 1, comma 2, etc. Now that minus infinity is an oddity in that normally you expect to have counting numbers for the plan. So I'll actually go to the next slide and come back. Here is the calculation for Bode's rule. And so if you put in the minus infinity for n, you just get 4 divided by 10, or 0.4 astronomical units. So 0.4 astronomical units is the distance predicted by this Bode's law. The distance from the sun to Mercury is 0.39 astronomical units. Pretty good match, right? And then you go to this next one, 0.7 astronomical units versus 0.72, 1 versus 1 for Earth, that's a given. 1.6 versus 1.52 for Mars, that's just a little off. 2.8 versus 2.78, that's how he found it. This Bode's law was determined by looking at the data from here to here without having this one. And so people looked at this pattern, saw this pattern is really good, except there's one thing missing. And so with that one thing missing, Giuseppe went looking for what could be at this location, and he found Ceres, which is really cool, right? When we talk about Neptune and Uranus, we'll talk about the same types of things going on. If we go on, you'll see that Jupiter, Saturn, like Mars, is a little off. Uranus, at this point, I'm willing to take that 0.4 and say it's still good. There is Neptune that is not predicted. It's at something that doesn't agree with Bode's law. And then there's Pluto, which agrees pretty well with the next one. And after that, believe it or not, we have Eris that is within shooting range of the next one after that. What is the reason for Bode's rule? Okay. There is no reason for it. Remember when we talked about science and pseudoscience and things like the differentiation is that science has to be based on scientific ideas. Bode's rule is not based on any scientific idea. It's just looking at a pattern. Now, patterns can be important. We have patterns that have been used to predict things like that light behaves as a particle with distinct energies. But when Planck observed that, he presented it to the world, and he felt really crummy about it because he had no reason for it. It was just, here's a pattern. Balmer was the person who came up with the equation to give us the energy levels for, well, actually, in his case, it was the wavelengths of the emission from hydrogen, but he didn't have a reason for it, he just saw a pattern. But we found reasons for it, and then it becomes good science when you find a reason for it. Well, this here, there's no known reason for it. There's no known reason why this should occur. And so scientists look at this as, well, what a coincidence that he found a pattern that there doesn't seem to be a reason for. Maybe somewhere down the line we'll find there is a reason for it, but right now there's no reason for it. So one would have to say, well, that was just serendipitous that Giuseppe found Ceres there where this pattern would suggest. And we'll see a lot more about Ceres later on in today's lecture. So in 1801, the first item that we now understand to be asteroids was discovered, Ceres. And soon they found that there were a lot more objects out there that were like Ceres. Not as big as Ceres. I think it's the very next slide after the one we just saw. Ceres is like 1/3 of the mass of the entire asteroid belt. So mostly they're small things. I downloaded a data file with the orbital parameters for all of the known asteroids so I could count this number, which obviously I had the spreadsheet count. I didn't go 1, 2, 3. But they had orbital information for 721,070 asteroids. That's a lot of asteroids that we have identified. But not all of them that are out there for sure. By using measurements of light going through the asteroid belt, it is estimated that there are at least 750,000 asteroids that are at least a kilometer across. Many of the asteroids, these 721,070, a lot of those are much smaller than a kilometer across. But it's estimated there are at least 750,000 that are at least a kilometer across, somewhere up to 2 million asteroids in the asteroid belt is suggested. 1.9, I think 0.9 to 1.9 was the firmest figure I found. 0.9 million to 1.9 million. It's a pretty big uncertainty range. There are 200 known asteroids that are at least 100 kilometers across. Now, 100 kilometers across, that's pretty big, right? That's here to Omaha, basically, or the other side of Omaha, was it? Council Bluffs. Basically, here to Council Bluffs is, there's 200 that are that big across, which are pretty big objects. Now, this statement here contradicts what the conventional belief was when I started teaching this class about 20 years ago. 20 years ago, the conventional belief was probably that there was something that was growing to be like a planet and it got shattered. And so we'll talk about where all of this stuff is believed to have come from. Once again, just the mass. Ceres is 1/3 of the total mass. The entire mass of the asteroids in the asteroid belt is believed to be somewhere around 4% the mass of the moon, or 22% the mass of Pluto, or 1% the mass of Earth. So it's not nearly enough mass to be a planet. Even Pluto, that got demoted because it couldn't dominate its own region, has a lot more mass than exists in the asteroid belt. Now, what's the number one question that Russell wants to ask about the asteroid belt? I'm asking everyone else what your number one question is. It's something he's mentioned 2 or 3 times. That we should go out and mine them, and we should destroy them, or maybe we should mine a planet and destroy it.
I never said anything about the asteroid belt.
Okay, you're just talking about destroying planets. Well, a lot of people talk about mining asteroid belts. You see it in science fiction, right?
The planet's not efficient.
Excuse me?
Just doing it on the planet.
Okay. Why would you mine them? Well, there are things of value there. There's gold, there's platinum, there's water. That's definitely valuable. And so why don't we do it? There's one really, really strong, compelling reason. It costs too much. Right? If you spend $10 billion to get $5 million worth of gold, you just lost a huge amount of money. Right? So it's too expensive to try to go out there and mine them. But it is an idea that, believe it or not, NASA is, keeping on the back burner of, if we can get it cheap enough, we could go out and we could get some more resources from the asteroids. And I've mentioned this before. If you go to Disneyland, you ride Star Tours, you're in the little transporting spacecraft, and they go through the minefield, right? How many people have been on Star Tours? Okay, this example does not work then.
Wait, is it a Disneyland or Disney World?
Well, they have a Disney World too. Pretty much anything they have at one, they have at the other.
No, Disney World isn't.
Well, it has that concept, but that's. California now has California Adventure with its own stuff. Disneyland, Disney World, those things are the same. Okay, so in the movies, asteroid fields, you have lots of asteroids, you have to weave and bob to get around them.
The Star Wars famous asteroid.
Yes. Well, it turns out the average space between asteroids is somewhere between 1 to 3 million kilometers. Not a whole lot of dodging and weaving you would have to do to go through the asteroid belt, because it's mostly empty space out there. If you look at that picture, that does not look like mostly empty space, does it?
It's because it's really zoomed out.
It's zoomed out, and in order to see the asteroids, they have to make them bigger than a scaled size would be. So there's not that many of them, or there are a lot of them, but they're tiny, don't take up that much space. Now, most of the asteroids are in this asteroid belt. Oh man, my artistry. This asteroid belt that is between Mars and Jupiter. But there are some out here that are called Trojans. Now, we all know the story of the Trojan horse. Once again, referring to Russell. Russell, I think, was telling me something about beware of large gifts filled, or was it you that was telling me that?
No.
No, okay. Must have been my son. I get too confused.
Really?
Yeah. So, you know the story of the Trojan horse, right? Well, these are called the Trojan asteroids because they're hiding in the orbit of Jupiter. They're in positions that are called Lagrangian points. And these Lagrangian points are places where you can have a stable orbit with the object. And so those asteroids are just stably orbiting in front of and behind Jupiter. And so those Trojans are a special thing. There are some others that you see that are outside of the range, but that's where most of them are. So the types of asteroids. There are three basic types of asteroids. There are subdivisions for two of these. That is, the C-type and the M-type have subdivisions. The M-type is pretty boring. There are brighter ones and dimmer ones and the normal ones. But the C-type is 75% of asteroids that we have discovered. The C stands for carbonaceous. What that means is that you have the surface is covered with, carbon-based material that's dark. So they have a really low albedo. What does the word albedo mean? Reflectiveness. So they have really low reflectiveness. So that makes them dark in appearance. That's why the next line is there, dark in appearance. So these C-types, they have things like clay in their surface. Stuff that we would identify as dirt-like material. And so they are similar to the types of material that we have in the upper, the crust of the Earth. Then you have the crust and mantle area. Did you have a question, Max?
Yeah, but you can finish this one.
Well, no, go ahead.
I was just wondering why, if they have a different theory for why there are asteroids, and I've noticed the different compositions and whatnot. Why? How do they think they all got there? Why are they so different?
That is why I'm going through this. So,
okay.
Yeah, I see where you're saying. Finish the slide. So the next type, the stony type. These are about 17%, and these are made of stone and iron. Eros is an example. Ceres was an example of the C-type. And so these, being stone and iron, they're much like, I suppose, the feet of the statue, right? Then we get to the final type, metallic. These things are pretty much iron. I don't know if you guys have been to Barringer Meteor Crater, but it has the largest piece that they've ever pulled out is an iron meteorite. It's about this big. I went there with a student, 15 years or so ago, and our tour guide said, and if you can pick it up, you can take it with you. And so Rainey and I had to try, and I was able to make the thing move. I wasn't able to pick it up, of course, but Rainey and I were all, hey, let's try it together. Whoa, 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 whoa. I went back there with my wife, and there was no such thing. You weren't allowed to try to pick it up. But that's the result of an asteroid hitting the Earth. That asteroid was an M-type, a metallic type, that came into the atmosphere. Before it comes into the atmosphere, it was an asteroid, and we will call it a meteoroid. What's the meteoroid? It's the thing that's going to become a meteor before it becomes a meteor. When it comes into the Earth's atmosphere, we have the meteor, which is the light that's given off. And we'll study this coming up just next week, I think. And then when it hits the surface, if something hits the surface, what remains is called a meteorite. So that meteorite was the remnant of an M-type asteroid. And there are only 8% of all known asteroids. And Cleopatra here looks like a dog bone. It's pretty awesome in my opinion. Okay, a femur. Anyway, this is Cleopatra here. This is Eros here. Notice Eros has lots of impact craters on it. I believe the theory is that Eros is actually a remnant of, excuse me, two different asteroids that collided and stuck together. We have up the top two examples of the C-type Ceres and Matilda there. So pictures of the different types. Question that was asked by Max now. How do they believe that these things came about? If you look at these, it actually gives you a pretty unified picture that I said is not the case. Remember when I started teaching 20 years ago, that's what they said was the case. That picture is that you had a reasonable, planetesimal, it's forming, and it starts differentiating. What's differentiation in the planet formation process? The more dense stuff, i.e. the iron, sinks to the bottom, and the less dense stuff floats up to the top. And so if you have a small thing, if it's small, it's not going to develop enough high temperature to melt the entire thing. And so the stuff in the exterior would not melt at all. The stuff that sinks down to the middle would melt. Stuff that's close would be partially melted. And you can take that and say, okay, so we have a partially differentiated planetesimal that then gets broken apart. That could explain these, because you would have the stuff that was in the core would become the M-type asteroids, right? Because partially differentiated, you have a lot of iron there in the core. And the stuff that has the stones and stuff, the stone and iron mixture, well, that would be from the mantle, the region above where it was melted but close. And then the stuff that has the carbonaceous would be the outside of the crust. So it's a picture that kind of holds up together. But, like I said, that's not the current belief. The current belief is, it didn't have enough mass, just couldn't have done that. It must have been something more like you have a partially differentiated object that was hit, but it's not actually something that was well into planethood. It was small, and you probably had a number of these small things. So it's kind of more like it was a pachinko game, a bunch of these little things hitting each other. Now, why didn't these things clump together and form a planet of their own? Right? I mean, we had lots of impacts with other planetesimals, and we still formed planets like Mars, Earth, and so on. Why did these form their own planet? Why did they clump together? The answer to that is the gravity of Jupiter is so massive, as it gained more and more mass, it pretty much stopped the ability of these to actually clump together, because it keeps coming around and pulling things and doesn't allow them to clump. So Jupiter stopped them from coming together and forming a single object. So, clicker question numero uno. How did asteroids in the asteroid belt form? Just repeating Max's question to you. Okay. We had not complete agreement here. So, Mr. White, let's hear your answer.
Wasn't totally sure from the question side on that, but I was just thinking about even what you were saying, how different views they had even 20 years ago when you were teaching and everything. So I went with C or B.
B. There were once a small single planet that was shredded by the gravitational pulls of Jupiter and Mars. Okay, now I did go through talking about a single planet. It could not have been a large planet. I know there was one person who said a large. It couldn't have been a large because, after all, the total mass is like 1% the mass or 22% the mass of Pluto. That's never going to be considered a large planet. But it could have been a small thing that was starting to differentiate. But here I had the thing that was really wrong about B is that it says that it was shredded by the gravitational pull of Jupiter and Mars. That is an idea that's been considered, but the conclusion was no, if you actually had an object that was held together, it wouldn't have been shredded by the pole being that far away. But it stopped them from merging when you had them broken apart. So the theory is they were once developing protoplanets, but massive Jupiter stopped them from growing any further. And you would have had lots of collisions, so that would cause shattering and breaking them into pieces. So there's a correct answer. Now, the shapes and size of the asteroids are interesting here. We have had since 2001 a few different encounters with asteroids. There you see in 2001 the near-Schumacher spacecraft orbited Eros. So we have some really good pictures of Eros because we've had something go take pictures of it. And then Japan's orbiter landed on Ichawaka. I looked at the NASA site, said the three that we have good pictures of, clearly they were saying the three that the United States is taking good pictures of, because Japan certainly would have taken good pictures of Itokawa. Yes, kawa means river. Ito, I'm not sure. I should know this. Anyway, so they actually landed on it, picked up some material, and came back. The Dawn mission left Earth in 2007. In 2011, it arrived at Vesta and orbited Vesta for about a year, a little more than a year. And after orbiting Vesta for a little more than a year and collecting as much data as they could on Vesta, it then headed out to orbit Ceres. And it's been orbiting Ceres since March of 2015. And so this the Dawn spacecraft has been learning a lot more about asteroids. And you might have seen things in the news asking, what in the world is that? And I've got pictures coming up on that. But we've been learning a lot more about these asteroids to help us understand, and it's from information like this that they now say, no, could not have been a shattered protoplanet. So let's look at Ceres. This picture here is a cutaway view of Ceres, similar to the cutaway views we've seen of the other planets. Zoom in there. They believe that it has a water ice layer under the crust. Why would they believe it has a water ice layer? Since we have the Dawn spacecraft orbiting, we can use the spacecraft to determine the density, determine the mass first, of Ceres very accurately, and see how gravity is affecting differently in different locations to actually map out where that mass is. Using that information, we can calculate the density of Ceres, and we find the density of Ceres is actually about the same as the density of Pluto. It's somewhere between the density of rock and the density of water. And so the conclusion with Pluto is that it must be like half rock, half water. Same conclusion for Ceres. That Ceres must have a lot of water, a lot of low density material in there to make it so its average density is so low. And so you look at that, believe it or not, that's pretty much what the Galilean moons, except for Io, look like as well. They have a surface on them. On the Galilean moons, it's an ice surface, whereas here it's a rocky surface. But below that rocky surface, they believe, is a lot of water, and then a core. So the diameter, 945 kilometers across. Now, 945 kilometers, we're talking pretty good size here, right? That's somewhere around 600 miles almost across. Now, 600 miles compared to the size of the Earth, that's small. But 600 miles is certainly bigger than any, well, I think any dimension you can take in the state of Nebraska is shorter than 600 miles. So, it's big. Probably somewhere ballpark of, well, less than Texas size, but,
Nebraska's pretty much a square, right?
No, we're elongated.
Lincoln's in the middle, right? Or was it a little bit?
No, Lincoln's right by the border. I mean, the border is Omaha, and we're only like 60 miles from the border. And we're like 400 miles from the other border. Okay, and I say like 400 miles. I don't know if you guys read the mile markers on the road, but yes, we are 400 miles from the other border. The albedo of Ceres is 0.090. Would you consider that a high albedo or low albedo?
Depends on what a high albedo is.
That was my follow-up question. Okay, that is a low albedo. Albedo, we've already established earlier today, we talked about it. That's the reflectivity. So it reflects 9% of the light that hits its surface. 80 or 91% is absorbed. So if light shines on Ceres, we don't get that much out of it. The low albedo. Why is that? It's because of the chemical composition of its crust. Max.
What is the Earth's albedo?
The Earth's albedo is somewhere in the ballpark of 0.3, a little above it, I think. The moon is quite low. It's about 0.12-ish. And this is even lower than the moon. Now you think about, the moon is really bright. It's really bright, not because it reflects light well, because it's hit by a lot of sunlight. So here's the bright spots on Ceres. What's making those bright spots? Does anybody know the answer? No, it's not pyramids making them. Does anybody know the answer to what's making those bright spots? Because if you do, you should call NASA. No. If it was carbon, it would be dark.
I said not covered.
Okay. Yes, it's not carbon because it would be dark. They believe that it's some kind of salt. They've done some exploration from space, not landing there, and they've identified certain compounds like it's ammonia rich in this region, and they found some magnesium sulfates. And so they believe that there's some salts here that's making the high reflectivity. And remember, this has an albedo of 0.09. It only reflects 9% of the light hitting it. These regions here have albedos on the order of 0.40. They're reflecting about 40% of the light that hits them. So 40% compared to 9%, that's more than 4 times brighter. That's why they look so bright. Now we also have pyramid structures. Where else do we have pyramids? Where?
Egypt.
Okay, Egypt, New Mexico. You said New Mexico or Mexico? Okay, good. I was like, New Mexico. I haven't heard of the ones in New Mexico. Yeah, Mexico, Egypt. We have pyramids here on Earth. Where did those pyramids come from?
People really want mountains.
People really want mountains. That's actually a good question that we don't have perfect answers for. We believe the Egyptians built their great pyramids, and we have time frames for them building them. Other people believe, no, it was aliens. The great Stargate franchise is all built on that, right?
The Google ships with that.
Yes, they're landing docks for the Google ship. That's right. Okay, but we have pyramids all over the earth. Basically, every culture has pyramids of some sort. Ziggurat here, whatever. And so that's. Excuse me? Excuse me?
Did they calculate pyramids?
I don't know.
They have this stuff.
Yes, they have Stonehenge. But we have pyramids all over. And we saw on Mars, actually, did I show you pyramids? I didn't have time to show you pyramids on Mars. But in that Cydonia area, there are also pyramidal structures. And now we have on Ceres pyramidal structures. If you want to believe that aliens did this, there's some mounting evidence there. Now, most of us don't buy into that. We buy into, maybe there was communication that we didn't know about between peoples. Maybe they had similar religions. There are lots of different answers. Some that are very congruent with the biblical idea of the Tower of Babel. People we're all one people and then they got separated, and they would have all had some basic understanding of history in the past and maybe of building designs. But the fact that we have pyramidal structure there is going to lead to interesting speculation. Of course, what do you think scientists believe?
It's a lot.
How big is that pyramid? Is it just a little? Because I can't tell from the picture like what the scale is.
Yes, I can't tell the scale either, but I can tell you that the entire planet is approximately 600 miles across. And so we're probably talking that my square is on the order of maybe 5 miles squarish. So, less than a mile. My wife's leaving. Bye. Okay, let's move on because that's just a speculative thing. It's interesting to look at. Here's Vesta. Vesta's diameter 525 kilometers, a little more than half the size of Ceres. It's 9% of the mass of the entire asteroid belt. So Ceres, did I have its percentage? I just put 1/3. This is 9%. There's not much left already. You've got these two are, the majority, well, not the majority, but a large chunk of the mass. And its density is 3.5 grams per centimeter cubed. Now, you just did a homework assignment where you were looking at the uncompressed densities of the terrestrial planets.
Isn't it like those densities close to that?
Yeah, they're close to that. So this, we presume, must be made of similar material to what the terrestrial planets are made of, based on its density. And so it's another object very different than Ceres, right? Different kind of composition. Asteroids can have moons. At least 200 asteroids are known to have moons. So this is the most famous one. This here is Ida, and this here is Dactyl. And you can see in the picture, there's Dactyl there. And then zooming in. So this is 2 asteroids, one orbiting the other. Now, most of us tend to think, that's impossible, to quote Ralphie. Is it Ralphie? I don't know. Chief Wiggum's son. Yeah, it's Ralphie.
I mean, anything can have a moon.
Anything can have a moon. What causes the Earth to stay in its orbit around the sun? It's the force of gravity. What causes the moon to stay in orbit around the Earth? Gravity. As long as you have gravity, you can have any two things orbit each other. But the speeds, the lower the mass, the slower the speeds are going to have to be. So in order for an asteroid with a fairly low mass to have a moon orbiting it, they're going to have a pretty slow orbit. What are you going to say, Russell?
We could get the moon a moon.
Yes, we could conceivably give the moon a moon. We could, in fact, we have sent up spacecraft that orbit the moon. That is an artificial moon, right? Because it's orbiting. There are also binary, what they consider binary asteroids, 2 things of similar size. If they're dissimilar, if one's much bigger than the other, they say it's a moon and an object. If they're similar size, they say it's binary, 2 of the same types of things orbit each other. So there are also binary asteroids. Yes.
Pluto does have a moon named Cerberus.
Okay.
How large are Ida and Dactyl?
I did not look it up.
Tiny.
Relatively small, but yeah, I did not look it up. Okay, you have a homework question about the Kirkwood gaps. The Kirkwood gaps are these regions in the solar system where we don't have any asteroids. We have the asteroid belt broken up by these gaps. And these gaps are set up by resonances. So I have a little simulator running here, and I'm going to simulate what happens for one of these gaps, well, for multiple. So let's take something that's in a 2-to-1 orbital resonance. What it means if it's a 2-to-1 orbital resonance, and actually I should go back to the picture here. Right here it says 2-to-1. What that means is in the time that Jupiter does one orbit, that asteroid is doing 2 orbits. And so we're going to look at the simulator just to see how that works out. So for a 2-to-1, I have the numbers for Jupiter there. Jupiter's semi-major axis is 5.20 astronomical units. And for a 2-to-1 resonance, we have 3.28. And I know you're supposed to find these, but you have to show how you found them, so I don't feel so bad about giving you the number there. And let's start the animation. So we see they were lined up, and now they've done just a little more than one orbit for the inner one, the asteroid, the gray thing's the asteroid, and just half an orbit for Jupiter. Let it keep going. And now we've done, I know I didn't stop it exactly right, but we've done one complete orbit for Jupiter and 2 orbits for the asteroid. How many times were Jupiter and the asteroid close together? 1 per orbit, right? 1 per orbit of Jupiter at the same location. And so what's going to happen is each time Jupiter comes to that location, the asteroid is also coming by. The distance is shorter. What does that do to the gravitational force if the separation is smaller? It increases it. And so the asteroid is going to get tugged toward Jupiter at this point every time. And what that's going to do is elongate the orbit so that it is farther away from the sun when it's close to Jupiter, and then closer to the sun when it's on the other side of its orbit. So it's going to make it more eccentric. But the problem with making it more eccentric is then it's going to start crossing the paths of other asteroids doing roughly circular orbits. And if it crosses the paths of other asteroids doing circular orbits, you can bet there's going to be collisions, and the collision is then going to make it find a new orbit. And so you can't have anything orbit in this position because it will be tugged out of that position, crash into other things, and find a new position. Now let's go to something that's a little more interesting. So the next one of the Kirkwood gaps is a 7-to-3 ratio. 7-to-3 was not one of the ones that you have to calculate. And that's 2.96 for this one here. That was close, but I'm actually going to enter it in. .96. So I started the animation with them lined up. Okay, they were lined up here. That was 3/4 of the way around for Jupiter. Now Jupiter's gone more than one. And there they line up again. That's 1.5 for Jupiter. It's going to always have the places where they line up being repeated. So the next one, okay, so we started with it where Jupiter's coming to now. Then it was down here. Then it was over here. The next one is up at the top. So with this 7-to-3 resonance, it turns out that there are only 4 locations where they line up. And so it's still going to work out with that 7-to-3 ratio for the orbits. You have these 4 locations where they line up and it gets pulled, and you're going to make the orbit kind of go wing, wing, wing. And once again, if you can make that orbit so you have a repeating force, you'll make it more eccentric, hits things, stuff gets pulled out of that orbit. So that's why the Kirkwood gaps exist, because of these resonances. So you keep pulling it the same way. There's the numbers. I know you can all look at the slide, see all the answers, but you still have to show how to calculate. And I didn't put the equations there. I only have 4 minutes left, so let's just do this comparative, and we'll start with Jupiter next class period. So I have a couple slides here on just comparing what we saw from the terrestrial planets. So the mass, which is, of course, how much stuff is present, and the size of a planet make a really big difference to the environment. If you have a planet that is small, then the ratio of surface area to material is larger and it cools more rapidly. If it's bigger, the surface area is proportionally smaller. You might remember I did the calculation of surface area divided by volume, and it was 1 over R. And so the rate at which it heats is or cools is proportional to 1 over R. Hence, bigger things cool more slowly. Now, the amount of heat leaving per second is bigger, but as a proportion to its total heat capacity, it's cooling more slowly. So bigger objects are going to cool more slowly, so they'll retain their molten core longer. In our work last night in lab, you saw the differences that having a molten core makes, things like magnetic field. Small planets can't hold their atmosphere very well. One of your homework problems, which, in case you care, there's all the math for it right there. Yeah, so after class, if you want, I can raise that so you can look at it and try to get your ideas on it. Or just talk to Max. Max knows all. But if you have a smaller planet, the escape velocity is going to be smaller, which means that gases are going to have a harder time being held onto by a small planet. Also, temperature. If you have a higher temperature, then the molecules of gas move faster, they can escape more easily. So temperature and size both play into holding on to the atmosphere. Mars is kind of in the middle, not too large and not too small, so it has kind of a unique space. It once had water, we believe, and an active surface, much like the surface of the Earth. Now it's cold and dead because, well, it's too small to hold this gas. Looking at the insides of the planets, all of the planets have a core, and even the moon here has a core, but the core of the moon we believe to be fully frozen. Why? Why would we believe the moon to be fully frozen at its core?
It has no atmosphere, so it can't retain heat, and it's small, so it lasts heat.
Okay, now those are tangentially good, but the primary thing is it has no planet-wide magnetic field. Now, does it rotate? Yes, it rotates once every 27.8 days or something like that, because it's tidally locked, and that's how long it takes to do one 360-degree orbit around the Earth. 29 point something days to go from new moon to new moon because it has to go farther. So it is rotating, and that's a lot faster than Venus rotates, actually. So it is rotating. If it had a molten core, it would certainly have convection because it's cool on the outside, as Max pointed out. And so it should have a planet-wide magnetic field. The fact that it doesn't means that that core must be frozen. Now, this shows a really tiny core. Why do we believe the core to be tiny? Well, actually, we have really good evidence for it. But first of all, by looking at the density of the moon, it suggests that it doesn't have much iron. A second thing is, yes, we've been able to actually map it because we've done a lot of study of the moon, and we know where the core is and how big it is by actually using things like take your lander up, crash it into the surface, look at the shock waves going through the moon. So we know it has this small off-center core. All the rest of these, Mars has this core, which we believe must now be frozen because it has no planet-wide magnetic field. Mercury has a core that is not completely frozen. How do we know it's not completely frozen? Because it does have a planet-wide magnetic field. And then there's Venus. Notice this is showing Venus with a molten core there, but it doesn't have a magnetic field. What's going on there? No convection is the belief, the theory we draw. All of these have a mantle region. Mercury has a much smaller mantle region. Why? Well, they think it probably is because it was impacted by something and a lot of its mantle got sent away, went bye-bye. And so it has a much larger core with comparison to the rest. So you look at these and notice the stages of planet formation. You accrete planetesimals, and then you have cratering, and that causes you to have flooding things and volcanoes. And then you have the slow surface evolution that the Earth is going through. Things like Mars and Mercury and the Moon, they don't have much atmosphere, so they don't have much going on the surface. And I guess I have to stop. Have a great long weekend.